So here's the formula for percent yield. And here's the story. You do a chemical reaction, and when you do a chemical reaction, no one does a chemical reaction perfectly. You're never going to make like the perfect amount, like completely pure products. So what you want to figure out is theoretically, like when you do like those stoichiometry problems, what you're actually calculating is the theoretical yield, and you're going to compare that to what you actually got from your lab data, what you actually got from doing the reaction in the lab. And then you're going to do divide that what you got in the lab divided by theoretically what you got, and then you multiply by 100 to get to a percentage. So getting to what a practice problem would look like. The practice problems look pretty similar to what you've been doing so far, but now you're going to see two numbers in like two given numbers here, kind of like what you saw with limiting reactants. So the hardest part I've seen with people today is trying to figure out which is my actual, which is my theoretical. So to do that, I think you got to use a little bit of common sense here. Think about what they are, like the actual yield is what you are actually making. This problem is kind of simple because they literally tell you it's the actual yield. Sometimes you'll see some other buzzwords, maybe add this to your notes. You'll see produce. So if you see produce, that'd be like a sign that this number is my actual yield. You'll see obtain. That's a sign that that's going to be your actual yield. But I think the easiest way is the actual yield is always the number that is a product. Meaning ammonia, that is our product here. So that's how I know the 14.9 grams. That's how I know that's my actual yield. Whereas the 13 grams, that goes with nitrogen gas. You know this number isn't your actual yield because nitrogen gas is a reactant. It's not a product. You're not producing nitrogen gas. You're starting with nitrogen gas. Okay. So looking at our formula here, percent yield, that percentage is going to equal actual yield. So 14.9 grams of ammonia, NH3, divided by theoretical times 100. So what we don't know from this formula is theoretical. So what you're going to do is you're going to use this 13 grams of nitrogen gas, and you're going to calculate the theoretical yield. Meaning, theoretically, if you start with 13 grams of N2, how many grams of ammonia, grams of NH3, would you make? In other words, to find this number, you're just doing like a basic stoichiometry problem like you have been doing. Yeah, Echo?
We have to balance the equations.
Oh, yeah, good, thank you. Remember, first thing you got to do is check that you balance the equation, which we actually haven't. Thank you for reminding me. So let's balance the equation here. We got two nitrogens in the reactants, only one in the products. So let's double the NH3. So now we got two N's on both sides. But then now 2 times 3 is 6 hydrogens in the products and only 2 in the reactants. So you're going to need to triple the H2. And then you'd be balanced. All right. Then using your map here, grams of X. X here is N2. Right? N2 is our X. So we want to go from here to grams of Y. Y being what we produce. Y is your ammonia. So ammonia is my Y. Nitrogen gas is your X. So when you're going from grams of X to moles of X, you're going to divide by the molar mass. So if grams of N2 is here, grams of N2 goes down here. The next unit in our setup here is moles of X, X being N2. So moles of N2 goes on top. When you're doing molar mass, it's always in 1 mole of something, how many grams? To figure that out, you're going to find nitrogen on the periodic table, and its molar mass is 14. So you do 14 times 2, because there's 2 nitrogens, and that's going to be 28 grams. Okay? And then if you got moles of N2 here, moles of N2's got to go diagonal. Okay? So right now on our pathway, we're here. We're at moles of X. So then we're going to use a mole ratio to get some moles of Y. So moles of Y goes on top. And we said earlier, Y, that's what you're trying to find, the molecule you're trying to find, that's ammonia. So moles of ammonia, moles of NH3 goes on top. So this step right here, the mole ratio step. This is why you have to balance the reaction. So there's a 1 in front of the N2, so you put a 1 there, and then a 2 for the NH3, so you put a 2 right there. Okay. All right. Now you got moles of NH3 here. Moles of NH3's got to go diagonal. Okay. And then on top, that's the next unit. So then grams of NH3, that's going to go on top here. So grams of NH3 goes on top. And then the numbers that go here, you're going to multiply by the molar mass. So molar mass of NH3 goes up top here. We're in 1 mole of NH3. How many grams there are? Well, let's calculate that. NH3 is 1 N and 3 H's. Molar mass of N is 14 grams plus 3 hydrogens, where each hydrogen is 1 gram for the molar mass. So 3 times 1 is 3, plus 14, that would give you 17 grams. So 17 grams, that's what's going to go on top for NH3. Now you know when you stop here because grams of NH3 is here, grams of NH3 is what you want to find. This unit has got to match the unit that the actual is in. Sometimes they give you the problem, they're going to give you the actual in moles. So when you calculate your theoretical would also have to be in moles. Anyways, to get this number, you're going to do 13. You can skip multiplying and dividing by 1. 13 times 2 times 17, and then divided by 28. And that gives you 15.8. 15.8 grams. That's going to go on the bottom here. That's your theoretical yield. So understand what this number is saying. This number is saying that if you're a perfect chemist, right, you're the best there ever was, you could make 15.8 grams of NH3. But you're not perfect, and you made 14.9 grams in the lab. So let's see how accurate you were. So you're going to do 14.9 divided by 15.8, and then multiply by 100 to get to a percentage. So your answer would be 94.3%. So that would be your answer for this problem. So decently long, but as I said, really this is the next step. Everything else has just been doing what you have been doing before. Let's do one more together, and then I'll let you start working. So this problem was giving me fits in first period because I couldn't read. I couldn't tell like what these numbers were. I did like a screenshot from somewhere, and in my head, when I screenshot, I didn't realize how poorly the resolution is. So this is C6H5, and then over here, this is C6. See, I already messed it up. This is C6H6. Excuse me. This is C6H5Cl. So, anyways. Looking here, first thing, let's balance the equation. That way I and you don't forget to do that. Now, you look at it and you're like, wow, this seems really complicated. But actually it's not, because you have 6 carbons on one side, 6 carbons on the other, 6 hydrogens here, 5 plus 1 is 6 hydrogens, 2 Cl's here, 1, 2 Cl's in the products. So it's actually already balanced. It's just 1s for everything. So that's nice. Everything's in the same ratio. Next step is figure out what is your actual. So which of these two numbers is your actual? And the answer is, well, which one of these is a product? 15.1, yeah, good, because C6H5Cl, that is a product. So that's why this number, the 15.1 grams, that's going to be my actual. So percentage is going to be 15.1 grams of C6H5Cl. Divided by the actual yield of what? Of C6H5Cl. So we got to find this number right here. That's what we're going to do for our calculation. So if we start with 10 grams of C6H6, how many grams of that product of the C6H5Cl can we theoretically make if you're like the perfect chemist? So using our map, I'm starting you here at grams of C6H6, and we got to find grams of Y. X is, X would be this. What you start with. Y is the C6H5Cl. So grams of C6H6 is here. Grams of C6H6 goes diagonal. Okay? So what we're trying to do is the next unit is moles of X. To get to moles of X, X being C6H6, we are going to divide by the molar mass of C6H6. So in 1 mole of C6H6, how many grams are there? Well, there is 6 C's and 6 H's. So we got to multiply both of them by 6. Molar mass of 1 carbon is 12 grams. And the molar mass of 1 hydrogen is 1 gram. So 6 times 12 is 72. 6 times 1 is 6. So 72 plus 6 is 78 grams. So 78 grams goes in the bottom here. It's your molar mass. And then you got to keep going. We don't stop until we get to grams of C6H5Cl. So moles here, that means this mole's got to go diagonal. Moles C6H6 goes diagonal. So right now, we are right here in our setup. Okay? So then now we're going to have to use a mole ratio to go to moles of Y. So my next unit here is moles of Y. Y being C6H5Cl. Okay? So when you're doing the mole ratio, the numbers that go here come from the balance equation. Now, because there's just a 1 as a coefficient for everything, it's just a 1 for both of them. So mathematically, this step doesn't really do anything for us. It doesn't change anything. Okay. Right now, we are here. We just got ourselves to moles of Y. So now you got one more step. You got to get to grams of Y. So if moles of C6H5Cl, that's going to go diagonal, so they can cancel. And then on top here is the next unit you're finding, which is grams of C6H5Cl. So to get there, you're going to multiply by the molar mass of C6H5Cl. So in 1 mole, how many grams there are? Let's calculate that. You got 6 carbons, 5 hydrogens, and 1 chlorine. So times 6, the mass of 1 carbon is 12. We have 5 hydrogens. The mass of 1 hydrogen is 1 gram. So 5 times 1. And then chlorine's molar mass is 35.5 grams. So the molar mass would be 6 times 12, which is 72. 5 times 1 is 5, so 72 plus 5 is 77. Plus 35.5, that would be 112.5 grams. That's our molar mass of C6H5Cl. Okay? So then to get our theoretical yield, to get this number there, you're going to do 10, skip multiplying and dividing by 1, 10 times 112.5, and then divide the bottom, divide by 78. So when you do that, you would get 14.4 grams. 14.4 grams. That is your theoretical yield. Okay, so theoretically, you're the perfect chemist. You would get that amount of C6H5Cl. All right, so then we do 15.1 divided by 14.4, and then times 100. When you do that, you end up getting 104.8%. That would be your answer. Now, what do you notice about this answer? Why is that answer peculiar? It's above 100. Yeah.
How can the
That's the question, right? Like, how is that possible, right? I told you, if you're perfect at chemistry, you get 14.4, and you're telling me, whomever did this reaction somehow got 15.1, what might be happening there? Because this could happen in a lab. This wouldn't just be like they made something up.
Is it because the theoretical is less than the actual?
Say it one more time.
Is it because like the theoretical is less than the actual?
Yes, the theoretical is less than the actual. That's why you got over 100%. But I'm saying, with that in mind, how could that happen in a lab? Like, what could be going on? What could have happened is some sort of contamination. Maybe there was leftover product in the test tubes and beakers. This actually happens like sometimes when like third period or fifth period does the same reaction from first period. First period didn't clean out their glassware very well, so they had some leftover product already in the test tube or the beaker. So that's how you could get more than what you could theoretically get. Anyways, so there you go. There isn't what I can where this could be. This could like the problems could get trickier. I don't even think trickier is the right word. Is they could give you the actual yield. They could give you this number. Most of the time it's in grams, but they could give it to you in moles or in molecules. In that case, you would not get to grams of C6H5Cl. You would get into moles or molecules, whatever the unit the actual's in. All right, I'll stop talking. Let you start working.